IV characteristics. In this video, we will explore the relationship between the current in amps and the potential difference in volts of different components through an IV graph, and have a look at the corresponding GCSE required practical investigation. Here is a contents list of the topics covered in this video. Refer to the description below for timestamps and summaries. The exact relationship between potential difference and current is different for different components and can be shown on a current voltage graph. As the potential difference, or the voltage, across a component is increased, the current also increases by Ohm's law, V is equal to IR. We can also show this relationship in an equation triangle. Now, we've talked about Ohm's law before. Conductors which obey Ohm's law have constant resistance, and their potential difference shows direct proportionality to the current flow. Looking again at our equation triangle on the left, we see that resistance is equal to the voltage divided by the current. A graph of the current against the voltage, such as in the case of an IV graph, must then be a linear line for an ohmic conductor. However, the resistance of some conductors changes as their temperature changes. These types of conductors are called non-ohmic conductors because they do not obey Ohm's law. In order to investigate the current voltage characteristics of a component, we'll need a simple circuit with a DC power supply, such as a battery, connecting wires and a variable resistor to adjust the potential difference across the component we're investigating. We'll also need a voltmeter in parallel across the component and an ammeter in series to make our readings. The components you'll need to study for your GCSE exam and investigate as part of one of your required practicals are a fixed resistor, a filament lamp, and a semiconductor diode. A-level physics students should also take a look at the A-level extension to this topic, which also covers thermistors and light-dependent resistors. Now, let's talk about how we take readings. But first, a student question.
How do I measure negative currents?
As negative current is simply current flow in the opposite direction, for our circuit, we just need to flip the orientation of the cell or battery. If working with a power supply, switch the two leads. Measurements at different potential differences can then be taken by adjusting the variable resistor between readings. This experiment can also be done at home. The University of Colorado Boulder have created PHET, or Physics Education Technology Interactive Simulations. One of these is a DC circuit construction kit you can carry out part of this practical with. Links to all resources are in the description below and in the pinned comment. Opening the PHET DC Circuit Lab, we can see that to the left of the screen are our electrical components. This includes wires, batteries, filament bulbs, resistors, and much more, and they can be very easily slotted together as seen in the video. Feel free to pause this video and take your time playing around with the PHET lab to make some simple circuits. To the right of the screen is resistivity and display settings. Here we can choose the values that we want to see on our screen, our voltmeter and ammeter to place into our circuits, and we can also control wire resistivity and battery resistance. We can switch from the realistic images of electrical components to their circuit symbol equivalents using the toggle in the bottom right corner. Let's now build our current voltage characteristic circuit. The circuit I'm building here is the same as the circuit that was shown earlier, with a gap being left for the component we will be investigating. I've set my variable resistor to 0 ohms. I'm going to set my power supply at 10 volts, a nice round number. We begin with our fixed resistor. I'm setting this to have a fixed resistance of 1 ohm. But you can try lots of different resistances. My settings are currently showing electron flow around the circuit. I can change this using the toggle in the top right to show conventional current instead. As expected, the conventional current is in the opposite direction to the electron flow. We can now use our variable resistor to take some readings for our 1 ohm fixed resistor. To take readings, we first set the variable resistor to give the highest potential difference and record the readings on the voltmeter and ammeter. We then adjust the variable resistor to change the potential difference across our component. We will record the new readings on the voltmeter and ammeter and then repeat the measurements, adjusting the variable resistor to decrease the potential difference slightly each time. The resistance is easily altered by clicking on the component and using the sliding scale. Let's transfer these readings to our IV characteristics graph. Plotting our values, we can see that there is a linear relationship between the potential difference and the current across our component. As expected of an ohmic conductor, our resistance is constant, and the gradient, current over voltage, is equal to 1 over our resistance.
What if the fixed resistor is of a different resistance? How will the IV characteristics change?
As the gradient is indicative of the resistance, by looking at Ohm's law, we see that different resistances should have different IV graph gradients. For an ohmic conductor like a fixed resistor, this gradient is constant. From the relationship between the gradient and the resistance of the fixed resistor, we can see that a lower resistance is equal to a steeper gradient on our IV graph. However, this linear relationship is dependent on the temperature of the resistor being constant. It is therefore important not to leave the circuit connected for too long, as it could then heat up. Let's now talk about our second electrical component, the filament lamp. The bulb contains a thin coil of wire called a filament. This heats up when an electric current passes through it, producing light. Unlike the fixed resistor, a filament lamp is a non-ohmic conductor. The resistance of the lamp increases as the temperature of its filament increases. Therefore, the current flowing through the filament is not directly proportional to the voltage across it. This is in violation of Ohm's law. Working with PHET, while we can see that the virtual lab does include a filament light bulb, the bulb does not show non-ohmic behavior. Adjusting the variable resistor shows that there is a directly proportional relationship between the voltage and the potential difference, making PHET unsuitable to emulate this part of the practical experiment.
Why are filament lamps non-ohmic?
As large currents run through the filament, it gets hot, causing atoms in the filament to vibrate more. This causes resistance to increase as electrons now collide more with filament atoms when flowing through. This makes filament lamps non-ohmic, as the resistance can vary. Let's now put our filament lamp into our IV characteristics circuit. We again take readings by adjusting the variable resistor to produce different potential differences across our lamp. Through plotting our readings, we expect to get a graph that looks like this. In this case, the current is not proportional to the potential difference. And as the potential difference increases, the current no longer increases as much. Now, moving on to our final component, the semiconductor diode. This is another non-ohmic conductor with an interesting IV characteristic graph. It again can't be modeled through PHET. Current in a diode can only flow in one direction. This is as it has a very high resistance in the other direction. However, even this one-way current only begins to flow once the threshold voltage is achieved.
Why are diodes important?
We know by now the usefulness of resistors, and filament lamps are an important source of light. But what makes diodes important electrical components? Diodes are extremely important in that they can be used to regulate current flow in a circuit. This is useful in making logic gates in computing and used as an indicator in LEDs. So let's now put our final component into our circuit and take some readings. we expect to see no current flow at negative potential difference and no current flow at positive potential difference until a threshold voltage has been reached. Beyond the threshold voltage, we can see that the current increases rapidly. An extra resistor can also be added in series to the circuit in order to keep the current low. This is to prevent damage to the diode. To measure this small current, a milliammeter may be preferable to a standard ammeter as it is more sensitive. And that brings us to the end of our required GCSE components. Thanks for watching our video, and be sure to try out the PHET Virtual Lab at the PHET Colorado website. Test yourself using the IV characteristics quiz linked in the description, and recap topics using the timestamps provided.